Prospect theory, reference point, which is malleable, which is frame and reference, which is frame dependent, framing dependent or context dependent. Concavity for gains, convexity for losses, and a steeper function for losses than it is for gains. That, however, doesn't actually change this. That still, you could take any option and you can go, I can evaluate that option independently of all the other options by using this. What they also said, and this is the vital bit, is that people, so let's go. If expected utility of a gamble equals the sum of the utility of outcomes times the probability of the outcomes, in prospect theory, we have, actually, let me go straight to cumulative prospect theory. I'll get onto that in due course. We say people use a different function. They use this value function to transform these, and the value function has that shape. But they also distort probabilities. So the probability that people ascribe to an outcome is not the objective probability. People make decisions as though the position of that outcome relative to all the other outcomes shifts the probability. So this starts to mean that the value of a given choice to me cannot be assessed independently of that choice in the context of, independently of the context of the other choices. And that brings us to the probability distortion. People make decisions as though they distort probabilities mentally. And this in cumulative prospect theory is what people are distorting, is they are distorting the cumulative distribution, the cumulative probability distribution. So if I have a cumulative distribution from 0 to 1, where 0 is this event is impossible, so 0, this cumulative being, if I rank all the outcomes from lowest to highest, from the biggest loss to the biggest gain, I rank them, and then I start stacking up the probabilities. So the lowest one may have a probability of 10%, the next one has another probability of 10%. Once I've got to here, it's certainty that I've got all outcomes included. What people do is, if I was being rational, if I was using probabilities objectively, my weighting that I ascribe to that cumulative probability should be a 45-degree line. I should be treating each probability as a probability. What instead I do is, for the extreme ones, I become very sensitive to changes in probability. And this can be put intuitively that shifting something from impossible to merely possible, to take its probability from 0% to 1%, has a much bigger psychological weight than moving a probability of something from 49% to 50%. Now, in expected utility theory, that should not be the case. If I increase the probability by 1%, it doesn't matter where the 1% comes in. What I do is I add 1% to the weight I give to that outcome. What you're saying here is that outcomes that are very bad are at the bottom of my rank ordering, and outcomes that are at the top of my rank ordering get a probability weight that is bigger than they should have. Or another way of putting it is I have diminishing sensitivity to probability away from the extreme outcomes. Now, if you think about a probability distribution, where are the extreme outcomes? They are in the tails of the distribution. So this probability distortion is basically saying that people make decisions in a way that would indicate that they are psychologically overweighting the tails of the distribution whenever they make a decision. And we can explain this, or we can give an intuition for it psychologically by saying that people face hope or fear. They have optimism or pessimism. So if I have optimism, I tend naturally to focus my attention on the really good outcomes, the really high returns I might get. So I tend to overweight those. On the other hand, I fear the really bad outcomes, so I tend to overweight those. And it means that we get this sort of curve. In the middle, I tend to underweight the probability of the middle outcomes because that curve is flat, and at the sides, I tend to overweight the probability of extremely bad outcomes and extremely good outcomes. And there's just a quote that I find quite useful from Enrico Di Sidua and Peter Wacker. So the attention given to an outcome depends not only on the probability on the outcome, but also on the favorability of that outcome in comparison to all the other possible outcomes. So suddenly, we've broken down this independence of choice of outcomes, where I'm now judging something relative to whatever else I see in that context. And this is what it would do to a probability distribution. So here, imagine this is the gain side of it. So I'm just looking at the probability of what happens above zero, above the reference point. If this dotted line is the actual density function, is the actual PDF of that outcome, what cumulative prospect theory is doing is saying that people actually act as though they have distorted this so that they suppress the probability of moderate outcomes and they explode or exacerbate the probability of extreme outcomes. Now, that clearly is irrational, because if I am trying to make a good choice, I want my assessment of that choice to be based on the best, most accurate possible probabilities. So if I am acting as though I'm constantly overweighting really good things and really bad things, it means basically I'm playing this game of odds where I'm constantly distorting the odds internally when I make decisions. Okay. Now, before we're going to move on shortly, just to start to set up the framework of how would this affect our portfolio theory approach. But it is interesting to ask first how, if we try to assess the degree of risk aversion in the market, what sort of level would it be? And this was done by Gregory Mankiw and Zeldis, I think. They asked this question. I've already used these numbers. Imagine that you've got a gamble such that there's a 50% chance that you get 100,000 and a 50% chance that you get 50,000. Now, the expected value of that gamble is 75,000. So if I was completely risk neutral, I would say I'm indifferent between you giving me 75,000 and me taking the gamble. Because these are in gains, most people are risk averse, and most people say, well, you know what, I'm going to accept a little bit less than 75,000 to take, rather than take that gamble. So if you come to me and you go, I'll give you 70,000 for certain, or you can take the gamble, I'll go, you know what, I don't want to run the risk of getting 50,000, I'm just going to take the 70, fine. The question is, what is your value of X? Does anyone have a sense of where they would go? How much would I need to pay you? Or what is the threshold above which you go, you know what, you're paying me too little. I'm going to play the gamble. I'm going to go for the 100,000. Does anyone have a sense or a stab in the dark at that? 60? 65? Okay. There's 75. Okay. These are all perfectly plausible answers. 75 would be extreme, because you're saying, I'm going to just play the expected value. But actually, in the context of your entire life, most people probably take too little risk in their life, because they partition things up into small accounts. And they go, I'm going to avoid risk in this account, and that account, and that account, and that account. And if I don't know if any of you are poker players, but you know the way to play poker mathematically in a rational sense is to go, poker is a series, is a portfolio of sequential bets over very long periods of time. This could be not just over this game, it could be over multiple games. And the rational way to play poker is to maximize expected value. Now, which that doesn't help you here, because you still would be indifferent between 75 and this choice. The question that Mankiw and Zeldis asked was, if we look at the equity risk premium, we look at the amount that the market demands in order in order to buy equities. So if I buy equities, I need to be paid for taking the risk. And that risk we can think of as the equity risk premium. So how much do equities outperform cash over long periods of time? And it is a surprisingly high number. And in fact, it is so high that if you were to apply, if you were to fit in an expected utility world, you were to fit a utility curve and say, what level of risk attitude is applied by the equity risk premium in the markets? And then you use that to calculate the value for X here. X would be 52,000. So that means that people would reject, well, basically, if I offered you 60,000, that was the lowest one we had here. If I offered you 60,000, you'd go, no, I don't want to play that gamble. You'd say, definitely, give me the gamble. If I reduced it and I said, I'll give you 53,000, you go, no, I don't want to take the chance. I'd rather take a certain amount. When we look at risk taking in the market as a whole, it is extremely, extremely high. Risk aversion, it is extremely high. And there are a number of reasons for this, but one of the most compelling was a paper by Shlomo Benartzi and Dick Thaler. Dick Thaler, the current Nobel Prize winner, who explored the notion of myopic loss aversion. And what they basically said was, if people are loss averse, they're acting as though they're not maximizing expected utility. They're acting as though they are trying to minimize the probability of loss. And these are two very different things. So if I was to look at equity markets over long periods of time, over 10 years or so, and I was to randomly choose any 10-year period, the chance of picking a 10-year period where you experience a loss in an equity index is less than 5%. Whereas if I was to look at it at a short period of time, over 1 month, equity markets go down about 40% of 1 month periods. So if people are myopic, if people cannot look to the long term, if they're making decisions, even if they're long-term investing decisions, but if they're making decisions psychologically focused on the short term, then what you are going to see is that people will be loss averse, and therefore this will exhibit itself in excess risk aversion. And this is what we see a lot of the time is the main cost to people of all these behavioral effects is people are, if they have money to put into work in the long term, are far, far more risk averse than we should be. Okay. So let's get to portfolio theory. Here is the standard model. Pretty sure you're all familiar with it. We have a two-dimensional space. On one dimension, I have expected returns from investing, and the other one, I have a measure of risk, which is typically the standard deviation of those returns. And the assumption here is that rational people want to be higher, and they want to be more to the left. I want higher returns, I want lower risk. Fine. Once I make those assumptions, once I have this space, I can take any possible investment, and I can find ways of trying to figure out what I think the risk and return of those investments are. There are better ways to do this. There are worse ways to do this. I could look back over the last 5 years, and I could look at historic volatility. I could do a big Black-Linterman model with forward-looking assumptions. I could use that to assess my risk. But I can pretty much take any investment, and I can place it in terms of what I expected returns to be and what I expected risk being. What I'm effectively doing is I am, in trying to approach investment, I'm asking the question, what is my best assessment of the distribution of future returns? And then I take the temperature of that distribution with two measures. What is the mean, the expected return, and what is the first moment? What is the standard deviation? If I am able to do that over many, many investments, I get to put portfolios together, and I get to jumble them in different ways. And some of those ways, because of the correlation structure, will lead to expected returns for a level of risk that are higher. Some will lead to lower. And I get to say, some of these portfolios are logically better than others because they get me higher returns for the same level of risk, or they get me lower risk for the same level of expected returns. That enables me to draw the efficient frontier. In the restrictive models of modern portfolio theory with a whole bunch of assumptions, I can say one of those portfolios has the highest slope if I draw a line from the risk-free rate to that portfolio. it has the highest Sharpe ratio. I could call that the model portfolio, and the two-fund separation theorem says that what I should do is I should never buy any of these other portfolios. All I should ever do is buy a mix of this market portfolio and cash, because that line from there to there, if I have costless leverage, of course it extends up, which I normally don't. But that line from there to there is my most efficient set of assets I can get, mixing cash with the market portfolio that has the highest Sharpe ratio. Now comes the question, which of those points should I choose? Up to now, all of this is about investments. It's about modeling my expectations of the future multivariate distribution of returns. Central to the question of which portfolio should I choose, we need a model of the investor. We need to say, to what degree is this individual willing and prepared to trade off risk and return? And so in the initial model, in Markowitz's mean variance assumption, mean variance optimization arises out as a natural consequence of expected utility maximization if I choose a particular utility function. And in this case, what that utility function is doing is saying, what is my indifference curve between risk and return? To what degree am I willing to trade off risk and return? And I am indifferent to low risk outcomes with lower return and high risk outcomes with higher return. And this curve is the curve that signifies my indifference. To find the portfolio from my available set that I want, I raise that indifference curve until I find the point of tangency with that straight line with a Sharpe ratio. Fine. All simple enough. In practice, it normally doesn't work this way. So in practice, we normally lose this bit altogether. You very seldom in portfolio theory have people talking about utility functions or indifference curves. Why? Because if I go out to the market and I do the sort of exercise that Mankiw and Zeldis were doing, and I go, let me look at how I can try and assess the level of risk attitude in the market today, and I do that again tomorrow and the next day and the next day, what I observe is that the observable risk attitude of the market fluctuates wildly. It goes up, it goes down, and we have times when the average stock has a PE ratio of 30. We have times when the average stock has a PE ratio of 15. That is reflective of huge shifts in the aggregate risk attitude of the market. So if I cannot assess this line, if it's so unstable that I have no idea how to parameterize that indifference curve, then what use is it to me? And typically what happens is we go, I'll throw it away. I can't measure this properly, I'm just going to toss it out. That leaves me with a problem. How do I choose which portfolio to choose when I have no point of tangency? I have no indifference curve to work with. And so what we often find is that we make some very arbitrary assumption and we go, well, a moderate risk investor should probably have an annualized standard deviation of around 9 or 10%. That feels about right. So what I will do is I will draw a line at the 9 or 10% level. I will look at my efficient frontier and I'll go, I found my optimal point. My optimal point is there. And what we've done is we've thrown away a model of investor preferences. In this we have a model of the investments, but we have no model of the investor. And we've made an assumption that that investor cares absolutely about achieving an annualized standard deviation of 10% regardless of the return level. And so if this is the Sharpe ratio I'd expect in an average market, what about a really boom good market where actually things are going up, my expectations are that I'm going to get paid more for every unit of risk that I take. In other words, the efficient frontier has lifted higher because the world is a nicer place and my returns expectations relative to risk have shifted. In this model, I find my new optimum point, which still has a standard deviation of 10%. Or in a bad regime, I go, what point should I choose? Now I'm not getting paid very much for the risk I take. So I find the 10% level and I go, that's the point I should have. The problem with this is that if I'm in a world where I believe that I'm going to be paid more, I'm going to get higher expected returns for every unit of risk I take, what is the rational thing to do? Take more risk. Because I'm going to get paid more for taking risk, so I should do that. If I'm in the world where I think, actually, the returns for taking risk are pretty poor, what should I do? I should pull back. I should take less risk. I should sit on cash. So by throwing out the model of the investor in modern portfolio theory, we've basically imposed a psychological assumption of what investors care about. I care about getting 10% standard deviation per year. That is completely unreasonable. It bears no relation to investor preferences whatsoever, and it bears no relation to expected utility theory. And what we should see is this. Here, I should be taking that level of risk. In a good regime, I should shift my risk-taking up, and in a bad regime, I should shift it down. The problem with this is our assumption here has been that this efficient frontier is really stable. I can measure it, I can draw it in ink. But this thing is really unstable, so I throw it away. And I end up with this story where I just go, I'm going to take here. Actually, the argument that over the course of these lectures that Arno and I are making, the argument I'm making is that actually the indifference curve is the stable bit. We can parameterize that indifference curve, and we can use it powerfully if we approach this, build it up in a behavioral way. The argument, although I'm not sure that Arno would put it this way, but the argument that Arno is going to be making is that our assumption that we can draw the efficient frontier with stability is the wrong bit. So that's the bit that's unstable and flipping around all the time. So we want to turn this completely on its head. Rather than say we draw the efficient frontier in ink and we have the other one just in pencil, the indifference curve, we're going to do it the other way around. We're going to say, let us put our effort into determining the right indifference curve, and then let us put our effort into figuring out where today's efficient frontier is, because they're going to be fluctuating and moving around the whole time. Okay, so Markowitz was not trying to do anything irrational whatsoever. He was an economist. He was well versed in expected utility theory. He came to mean variance analysis, but mean variance optimization is entirely consistent with expected utility theory. However, it's consistent with expected utility theory only under special conditions. So either, because what mean variance basically says is I can take all the whole complexity of the multivariate distribution of future returns, I can take the dependency structure, all of that stuff, and I can distill it down and draw it in a two-dimensional space with risk and return. Okay? So that would be a valid thing to do if one of two cases hold. One, it would be valid to do if every distribution out there was Gaussian. If I could describe the distribution just through two parameters, one of which was expected returns, the mean, and the other is the first moment, the standard deviation. However, we know that returns aren't Gaussian. Some of them approximate it, but we know that there are fat tails, there's kurtosis, there's skewness, there's all sorts of stuff going on. And even if the returns for our standard instruments were Gaussian, through structuring, through use of options, we can construct instruments that have very non-Gaussian distributions. So Markowitz mean variance analysis works completely if I assume that all the risk in the world can be described through just the mean and the variance. If that is not the case, then I can still rescue mean variance analysis if I make the assumption that investors only care about mean and variance. Because if investors don't care about skewness or kurtosis, then as long as I'm optimizing for the highest mean and the lowest variance, I've completely described investors' preferences because they don't care about anything else. Now, it turns out that we can do that. If I were to write the utility function on wealth levels as a quadratic utility function like that, it falls out of that if investors have quadratic utility, then they do only care about maximizing return and minimizing variance. They don't care about anything else. So here I have a quadratic utility function, and what it does is it says I don't have to have normal distributions in there. I don't assume that the world is Gaussian. I assume that people only care about a Gaussian trade-off. Okay? Now, is that a reasonable assumption? And the answer is no, for a number of reasons. Okay? One of those reasons is the quadratic utility function is non-monotonic. If I accept that investors have a quadratic utility function, and by the way, the quadratic utility function is the only family of functions for which this is true. Any other utility function, and investors care about something other than just mean and variance. They care about other things. So if I optimize on mean variance, it means my optimization process is not maximizing expected utility. It's maximizing some subset of expected utility. So if utility is quadratic on wealth, it's non-monotonic. There is a point above which, if I make that assumption, I am effectively saying that above a certain point, utility will start decreasing as I get wealthier. Okay? Above this point, as I get wealthier, I actually get more and more miserable. Now, that may be true of a very small subset of the world's population. I very much doubt it is, but to have non-monotonicity and the function that is at the heart of our portfolio optimization is a behavioral assumption that is extremely strong and extremely unjustified. The other problem here is we have to look at the Pratt-Arrow measures of risk aversion. So, risk aversion in utility theory is defined by the degree of curvature in the function. The more concave my function, the more there is going to be a difference between the utility I place on the expected value and the utility I place on the gamble. So Pratt-Arrow have these measures of absolute and relative risk aversion. So absolute risk aversion is simply minus the second derivative on that divided by the first derivative. So this is a standardized measure of the curvature of the utility function. And I'll get to what these mean because that's important. And relative risk aversion is exactly the same thing, but it is normalized for the wealth level. Like that. Okay. Let's put these intuitively because you've probably all come across this before, but the intuition is really important here. Absolute risk aversion says that if I have a gamble for plus or minus 10 pounds on a flip of a coin, 50% plus 10 pounds, 50% minus 10 pounds, absolute risk aversion, if my absolute risk aversion is constant, it says that I evaluate that gamble in exactly the same way, whether I have 0 pounds to my name or am I a billionaire. Elon Musk, if he has absolute risk aversion, if he lost all his money tomorrow, would be equally willing to play a gamble for plus or minus 10 pounds than he is today. Relative risk aversion says if it's constant relative risk aversion, says, hang on. So absolute risk aversion and relative risk aversion, right, says that I am equally willing to play a gamble that is plus or minus 10% of my wealth, for example. So if I had a gamble right now that was, if it comes up heads, I get an extra 10% of my wealth. If it comes up tails, I lose 10% of my wealth. It says that as I become wealthier, I am equally willing to play that gamble for 10% of my wealth. The 10% obviously changes. Now, the reason this is important is we can use these to test the justification for the utility functions that we choose. So quadratic utility, if I take that formula and I use it to calculate absolute risk aversion and relative risk aversion, what we will see is, where are we? Let's do absolute first. It says that, no, let's do relative first. It says that my relative risk aversion is increasing. Now, what that means is, as I get wealthier, I get less and less likely, increasing,